Okay, so now what we're going to do is start talking about chemical physical changes. But before that, I want to sort of talk a little bit about just the properties of the different states of matter and how they're different. Okay, so there's three physical states of matter that we often hear about. There's the solid, the liquid, and the gas. And for water, that would be ice, would be the solid, right? And then liquid water, we just call it water. And the gas is not actually steam, but it condenses to form steam, and that's what you actually see. Actually, gaseous water vapor is or gas molecules floating around that you don't actually see those. Okay, now if you want to see it, like for example, be able to look at it and see that it's clear, all you need to do is, if you have a glass lid on a pot and you put water in it and you start it boiling, you'll notice that when you pull the lid off, all of a sudden steam forms. The reason the steam is forming is it's condensing the water vapor and forming little droplets, and those little droplets are actually the steam that you're seeing. But if you put the lid back on and you look at it, actually what you're looking through is water vapor. There's actually just a clear layer of water vapor above the liquid as it's boiling. So I want you to keep those things in mind as we talk about these different states, okay? Because it'll help you sort of understand how the properties are related to the states. So if you think about solid water, right? It's weird to talk about it like that, but ice, right? It has its own shape. So it's a definite, what we would say for that is that it has a definite shape. And it's its own shape. Now, when you take liquid water, or like my soda here, I'm drinking a Diet Dr. Pepper, right? The liquid doesn't have its own shape. Like if you take a glass and you flip it over on a table of water and you lift it up, right, it just goes everywhere, right? So the liquid actually takes the shape of its container or conforms to the shape of the container. So it takes, let me write this, takes the shape of its container. Now, the gases are a little bit trickier, right? But you're familiar with gases. You see them all the time. The ones that we're most familiar with, the ones we think about anyways, are like a helium balloon, right? If I asked you where the helium was in the balloon, right, I think you understand that the helium fills the entire inside of the balloon. So whereas a solid has its own shape, a definite and its own shape, liquids take the shape of their containers, gases fill their containers. So I'm just going to say fill the space. Mostly because it's shorter than the word container, and I don't want to have to try to write that in there again. Now, the solid has a definite volume, right? So it's also the same. I'm just going to say definite for that again. Liquids occupy whatever volume that they're in, so they also have a definite volume. But gases fill any container they're put in. So think about perfume, right? When somebody walks in and they're wearing perfume or cologne, right? And they walk into a room, I don't know if you think about this, but what's getting to your nose when you smell it, those are molecules of fragrance that make up the perfume. And if somebody wears perfume or cologne, the odor generally will fill the entire space that they're in. In fact, if they go to a bigger space, the odor might become more dilute, weaker, right? But it'll still fill the entire space. So again, as far as the volume of a gas goes, it's kind of variable, but again, it fills the space of the container that it's in. So it's the same kind of thing. Now, before I talk about compressibility is the ability to squish it, right? Solids and liquids and gases are very different in how they feel. But let's think about how the atoms are spaced. Now, in a gas, if you think about the way the atoms fill up the space of a balloon, right? They have a lot of spacing between atoms. Now, you can think about liquid water and ice, okay, in terms of the atomic spacing and how they relate to each other. If you take liquid water and you freeze it and it turns into ice, the volume changes a little bit. In fact, ice will take up more volume for the same amount of water, but they don't change that much, right? So what we know about atomic spacings in solids and liquids is that the atoms or the molecules that make them up, in the case of water, it's molecules. The molecules are really close together. So this actually affects the compressibility. So what compressibility is the ability to take the substance and squeeze it into a smaller space. Now, for solids and liquids, because the atoms are really close together already, right, it's hard to get them to go any closer. So compressibility is very low. And you would know this if you've ever done a belly flop or fallen and just like hit your face on the ground. The ground, or when you do a belly flop, the water, even though it's a liquid, is not very compressible, and that's why it hurts when you hit it, right? Now, on the other hand, if you have an airbag, right, and you jump onto an airbag like a mattress, you notice how it just sort of squishes around. It's much more compressible and actually much more fluid, so it moves out of the way from where you fall. So compressibility of solids and liquids is low, and the compressibility of gases is high. This is why, like when you get air pistons inside of like shock absorbers, that's why we use air, because the air is compressible and is able to squish in and expand back out easily. Now, there's two kinds of solids. We talk about crystalline solids and amorphous solids, and the definitions are there below. But in solids, the particles are close together and stuck together, right? So when we have a crystalline solid, what it means is that the solid, the particles of the solids, for example, gold or a carbon like in diamond, right? The particles are arranged in a regular repeating structure. Okay, you could think of oranges in the market. You know how they stack the oranges up, and they're all about the same size, right? And they'll make little pyramids out of them. That's in fact, if you look at the atomic level at elements like gold, you'll see those same kind of packing patterns in gold. So they line up like this, and then another layer lines up like this. You can sort of imagine these are oranges, right? And another layer lines up like this. And then, if you wanted to build this out, you could put another one here, another one here, another one here, and you could build layers and layers and stack them up that way. That's why the oranges don't just fall all over the place all the time. Of course, if you pull the bottom one out, it will, but don't do that. Anyways, so this is what we mean by a regular repeating structure. Now, amorphous solids, those are things like glass, plastic, and rubber. Don't have that regular interaction between the atoms or molecules of the solid. So what that means is, for a crystalline solid, when you melt it, it turns out it melts at a single temperature. Because all the atoms are held together in exactly the same way, when you heat it and it gets just to the right temperature, all of those bonds that are holding them together fall apart and it melts, okay? And they'll go directly from the solid state to the liquid state at what we call the melting point. Now, you know that plastics and waxes and glass are different because when you heat them up, they get soft and they don't actually they'll melt if you can get the whole thing hot enough. But in the process of heating it, you can feel like a candle, for example, if you leave it out in the sun or you heat it up, you can feel how it gets soft, right? That's an indication that that's an amorphous solid. Another indication would be that if something's, like for example, if water was an amorphous solid, Like if you took a piece of ice and heated it for a while and then hit it against your head, it would be soft, right? But I think you all know, been hit by a snowball or something, you all know that's not the way it is, right? So amorphous solids are different, and they don't have what we call long range order. They're not organized like these are. This is ordered, right? And then they also, the other thing that makes amorphous solids interesting is they don't have a single temperature at which they melt, but they melt over a range and they get soft. So like beeswax, right? When you heat up beeswax and it makes a putty, right? That's an amorphous solid. So liquids are like solids and the particles are close together, but they're not stuck together. So they're able to move around each other. So if you think about at room temperature, right? Water is a liquid, but this can is a metal, right? So this is a solid at room temperature, and the reason it's a solid at room temperature is because the attraction between the molecules is so strong that they can't move away from each other. But the liquid on the inside doesn't have as strong an attraction. The molecules aren't as strongly attracted, so they can move or freely flow around each other. So liquid particles are close together but not stuck together, and the particles have enough energy to move past each other but not far apart from each other, so there's still some attraction between the molecules. Now gas molecules are very far apart and moving fast. And so, you can't see gases in the air, but if you had, for example, helium from a helium balloon in the air, it's probably moving about 400 or 500 meters per second. Now, the reason it's not killing you, because if you understand what 400 or 300 meters per second even means, you could imagine a football field's about 100 meters, right? So if you're going 100 meters per second, you travel the span of the football field in 1 second. That's really fast, right? But the reason the gas molecules aren't like killing you is because they don't have any mass. If a person hit you going that fast, or if a car hit you going that fast, you would just be devastated. But gas molecules, even though they're moving even faster than that, don't have any mass, so they just bounce off of you, okay? But there is a lot of space between atoms or molecules of a gas. Now, I'm not going to really spend time talking about these last two, but these are sort of newer states of matter. One's the plasma, which we find in the sun. And then there's another one that's interesting that Einstein proposed. Like Einstein was, Albert Einstein was a really bright guy and had a lot of neat ideas. But one of them was he said at low temperatures, unusual things would begin to form. And he predicted these, and it wasn't until just, 10 or 20 years ago, we started seeing these things scientifically, being able to study them. Okay, one more thing about solids and liquids and gases that I always like to talk about, but they don't really talk about it much in the book, is the energy relationship for a substance, okay, and its state. So let me draw something for you here. So I'm going to start with the liquid or the solid at the bottom. All right, and if you take ice, and again, ice is a good one to sort of work within your head as you try to solve these kinds of conceptual ideas, right? If you heat it up, you're adding energy. So heating is increasing energy. So if you heat ice, what does it do, right? You kind of know, right? It melts. And so then you go to the liquid. What does that inherently mean? It means the liquid state is actually higher in energy for water than the solid state. That energy is in the form of motion, what we call kinetic energy, and the molecules are actually moving around. Now, they don't have enough energy to move apart from each other because that would be the gas. But if you continue to heat a liquid, what does it eventually do? It begins to boil. And when the liquid boils, what it's actually releasing is molecules of the gas. And so the gas state is up here. And so heating increases energy, and we think about the hierarchy of energy for a substance. Solid of a substance is always at a lower energy than the liquid, and the liquid is always at a lower energy than the gas. Okay, so let's talk a little bit about changes in properties. Okay, so changes are either physical or chemical. So changes are either chemical or physical or chemical. So a physical change is a change in the physical state of something. Okay, so for example, if I took a rock and I crushed it, right, that would be a physical change of the rock. It's still the same materials that made up the rock, but it's now in a different sort of state. Rather than one piece, it's broken up into small pieces. But physical changes are also things like solid, liquid, gas changes. And we call those phase changes. The thing about these phase changes or physical changes is that during the process, nothing new gets made. So H2O as solid is still H2O, ice, right? As liquid water, it's H2O. And as gas, it's still H2O. It's not separate hydrogen and oxygen. That's a common misconception. But as you heat water and it begins to boil, you're just making H2O gas molecules float around in the air. Okay, so there are names to these phase changes, these physical changes. And so what I wanted to do is give you those names. I'm going to create a diagram in here. It's going to be organized the same way that I just showed you. I'm going to put the solid at the bottom. Okay, I'm going to put the liquid at the middle. And at the top, I'm going to put gas. And I'm going to fill this thing up. So now what I'm going to do is blow it up so we can look at the whole thing. And remember, that's from lowest energy to highest energy. So if you heat it, you can go from the solid state all the way to the gas state eventually. And if you cool it, you can go from the gas state all the way to the solid state. I mean, that's what your refrigerator does when it makes ice, right? So there we go. Now, when I go from solid to liquid, okay, so this is not complicated. It's typically called melting, right? So you know some of these words. Another word for it, though, which is not as common, is called fusing. And it's called fusing or fusion, not to be confused. There's a nuclear process called fusion, but not to be confused with that. It's just that when you heat the solid or you heat ice, what does it look like it do? It looks like it sort of fuses together to form the liquid, so that's why they call it fusion. Okay. Now, if you go from liquid to solid, what do you call that when you put water in the refrigerator, in the freezer, right? We call it freezing, so that's freezing. There's not a real fancy word for that one, thankfully. And liquid to gas is generally called vaporization. Boiling is vaporization at a specific air pressure. Okay, so what we'll generalize though is whenever you go from liquid to gas, because that's what happens when you're boiling, we'll call that vaporization, and then you can go the other way. And what do you call that stuff like when you take a shower and all that liquid, right, is on the walls? Right? We call that condensation. That's actually what it's called condensation. Now, a couple of other ones that are not as familiar to people, but you're familiar with it, you just don't know it, is when you go from solid to gas or gas to solid. And the solid to gas is called sublimation. And actually, you see it happen all the time in your freezer. This is a very common example anyways. When you get freezer burn on the food, it's not that the food ever got above 0 degrees Celsius or 32 degrees Fahrenheit, because the freezer in your freezer should be much lower than that. It's that the gas molecules, right, that were... So think about it like this. You have a piece of steak. I don't know how to draw it very well. So that's my steak. Looks like a guitar or something. Anyways, and then you have ice. You froze it, right? So basically, you have ice on the surface. What happens is it goes directly to H2O in the gas phase. This is H2O in the liquid state. or solid state, I mean. And so it's kind of like vaporization, but it's directly from the solid. So we call that sublimation. And that's actually how stuff gets freezer burned in your freezer. Now the other part is, if you've ever noticed, like if you take a piece of a glass, like a mug, and you put it in your freezer, right? And you're going to make root beer floats, right? And you pull it out, and what happens to it, right? It gets all frosty, right? Well, what is that frost, right? That frost is just water vapor from the air, and it's directly going from the gas state to the solid state and depositing on the glass, and so we call this deposition. So new words, learn something new every day, right? So we have melting or fusing, with two terms for the same thing. Vaporization going up, sublimation going up. So those are all processes that have to absorb energy. And then we have gas to solid, or gas to liquid, and liquid to solid, and those all have to release energy. Remember, we talked about the solid, liquid, and gas being at different sort of energy levels, the liquid being higher than the solid, the gas being higher than the liquid. So there's terms related to the energy. I really tie this in later, but when you require energy, when you have to absorb energy, we call that endothermic. Because to go up, you have to absorb the energy. And if you're going to go down, you have to push the energy out, so it's exothermic. So you don't think about this, but when you go from the liquid state to the solid state, that is when you're freezing water, that's a process that has to release energy. And that's why your freezer has to work so hard when you put water inside of it, because it's going to take the energy out and it actually puts it through coils, and you can feel heat coming out of the back of your freezer. That heat is the heat required to cool the items in your freezer. That's required to be removed to cool the items, that is. Now, we have physical properties, there's physical changes, and there's physical properties. And these are things we observe during a physical change. So the crushing of the rock that I talked about before, the hardness of the rock is the physical property that you might measure for that. For water or for liquids, we have something called the boiling point. And when you go from liquid to gas, that's the temperature at which bubbles begin to form in the liquid. And so we call that the boiling point. Okay, and that's for an atmospheric pressure of 1. So we haven't covered enough of chemistry to talk about that very much, but at atmospheric pressure, water boils around 100 degrees Celsius. Now, the melting point is also the freezing point. So the melting point and the freezing point are the same temperature. So I have this is a thing I got for coaching. It's a Yeti, right? And if I put ice water in this tonight with some ice in it, right, that ice will begin to melt. And that if I measure the temperature in the morning and I measure the temperature at night, provided that the ice hasn't melted, that temperature, the evening to morning temperature, will be exactly the same. That's because water, and it'll be close to 0 degrees Celsius. That's because water melts at a constant temperature of 0 degrees Celsius until it's all gone. So, and you can try that if you have a thermometer that will measure that, like 32 degrees. Put this thing about half full of ice and water, stir it around, measure the temperature, then put the lid back on. Put it out to the side table, or you can even, actually, they're so good that you could leave the lid off and it still works. And you can put the thermometer back in the morning. Make sure you mix it up and it'll still be the same temperature, as long as there's ice present. Okay, so that's what we call the freezing point or the melting point of water. And these two numbers, 100 and 0, I want you to remember because they're important numbers, okay? Now, chemical changes always result. So we talked about physical changes. Now we're going to talk about chemical changes. Physical changes don't make anything new. It just changes the state. Chemical changes change the substance. So this is when we think about chemical reactions, when we're making new stuff, right? That's a chemical change. Okay, so I actually paused the video because I start talking faster and faster, and I need to slow myself down, so I pause and I take a few moments. All right, so um, sorry. When we're talking about chemical changes, we're always forming something that's new. So it's it's kind of hard to explain like how you know a chemical change happens because there's so many ways. But there are some simple signs of a chemical reaction, and I list these in the lab video for this later this week. But the common signs are color change. It doesn't mean it has to be a chemical reaction, but a color change of a substance is often the sign of a chemical reaction. You can have a formation of a gas. Now, you can't necessarily see a gas, right? We talked about water vapor. You can't necessarily see water vapor, but you can see or oftentimes smell the effect of a gas, right? If you have, like, my son had uh, about 6 or 7 of those Snapware lid food containers in his car for the last half of the month. And if you took one of those containers and you took a container of like fresh food and you opened it up, you could smell the chemical change. What you're smelling is the decomposition. That's a chemical reaction of the food, right? So you can form a gas. You might not see it, but you can definitely smell it. We made them take them all outside and hose them off. Anyways, so there's color change. There's gas form. There's I'm debating on whether or not I should say which sun it is, but you can form a gas, you can have color change, it can release heat. Okay, these are all things that you'll have to remember. It's not necessarily in this chapter, I think, but it's an important way that we recognize whether or not a chemical change has taken place. And the last one is you can form a precipitate. Form a PPT, like precipitate is what that stands for, from, says form a precipitate from clear liquids. Okay. Now that one we'll have to do so you can see it when you watch the video of lab later this week. You'll see precipitates form. That'll make more sense. So those are sort of the 4 common signs of chemical reactions. So let's look at some of these, right? And classify them as chemical or physical changes, and maybe we'll discuss a little bit about the property that goes along with that. Okay, but the combustion of hydrogen and oxygen to form water, or it could have been propane to combustion, so that's burning, right? Combustion means burn. Is that a chemical or physical change? Well, what happens when you burn propane, or what happens when you burn hydrogen? It releases heat, right? So this is a chemical reaction. If you have silver, like silverware, and you polish it up, make it all look nice, and then you set it aside, what happens over time? It typically turns sort of a gray color, right? That's a sign, the color change is a sign of a chemical reaction. So this would be a chemical reaction. Now, sublimation of water we just talked about, so you should get this, and we just talked about in the last section in physical changes. So this is a physical change, right? And so those are some of the ways that you can tell that a chemical reaction has taken place. We have these indicators of a chemical reaction. They don't always mean that there's a chemical reaction, right? But, right, you see a color change, or you have heat released, or gases formed. Like I say, you can't see the gas, but it is a sign of a chemical reaction. So now what we're going to do is talk about properties, and basically properties occur, chemical properties occur when a chemical change takes place, and physical properties occur or are measured when a physical change takes place, right? So I'll just sort of just say something real quick. When you see a question like this, it's just trying to throw you off a little bit. It's just asking whether the bronze color of copper, right, is a chemical or physical property. And since it's that way all the time, that copper has that sort of bronze color to it, that's a physical property. Right. Color is typically a physical property, but a color change is an indication of a chemical, Yeah, color change is an indication of a chemical reaction. I think I said that right. Okay, so hydrogen's explosiveness. So hydrogen gas, if you light it on fire, will explode in the presence of oxygen. So the explosiveness, the description of the chemical change is the chemical property. Okay, the shiny appearance of silver, again, right? Trying to trick you a little bit, the shininess of silver is a physical property. If it changes in color, that is a chemical change, right? And then the ability of dry ice to sublime, that's change to solid directly to vapor. So sublimation, right? That's sublime. We talked about sublimation over here, right? So that is a physical property of dry ice. In fact, I don't know if you know this, the reason they call it dry ice is because it goes directly from the solid state to the gas state and never goes through the liquid state.